This podcast is going to review oxidation numbers. On the screen is the oxidation chart that we used in science class. As you can see, this is the same one you added to your science notebook. The charges for each of the various groups, that's the columns in the periodic table, are listed above, and those are the most common oxidation numbers. The center section here, with the transition elements, these are a variety of elements that have multiple oxidation numbers. Notice that these are the most common oxidation numbers that are listed on this chart. Some of them, such as nitrogen, could either have a 5+ charge or a 3- charge. Our chart shows that some of the basic trends that we get with oxidation numbers. The elements found in the first column, also known as group 1 or the alkali metals, have a +1 charge, meaning that they end up having one electron removed, causing them to have an ionic charge of 1+. The group to the left, the one with a 2+ charge, those are our alkaline earth metals, and they lose 2 electrons. So if an ion has a positive charge, it's lost an electron. If you look on the other end of the periodic table, in group 17 are halogens. They tend to gain electrons. When you gain electrons, you become negative. And if you look at the noble gases, they have no charge because they are unreactive. You could be asking yourself, why should we worry about oxidation numbers? Well, they're going to tell us a lot about how an atom is going to react. Remember, we have our octet rule. The octet rule states that there should be 8 electrons in the outer shell in order to have an atom that will no longer react. Now, how many electrons are going to be needed to fill an outer shell? We can look at something called the valence electrons. So let's look at an example. We look at an oxygen atom. Oxygen is in group 16. It has 6 valence electrons. We know this because it is 6 columns from the left side of the periodic table to the right side. And it needs 2 more electrons to fill its outer shell. We know this also because there's 2 columns to its right. When we draw a electron diagram for oxygen, we can add those 6 valence electrons like so. When we do, we realize that there are 2 spots left open, just like when we look at on the periodic table, that there are 2 spots unfilled trying to get closer to the noble gases. In a chemical reaction, oxygen would like to obtain 2 more electrons. So either by ionic bonding or covalent bonding, oxygen will fill those spaces with electrons. If it's ionic bonding, because oxygen gains 2 more electrons to oxygen, it gets a total of 10 total, because it's got 2 electrons in the first energy cell, and total now of 8 in its next energy cell. We know that oxygen only has 8 protons to do its atomic number. That leaves it with a total charge of -2, which is its oxidation number. Let's look at another example. If we look at the element magnesium, it has 2 valence electrons. We know that because it is in the second column of the periodic table. It has 2 electrons, valence electrons, and to complete its outermost shell, it would need 6 more to make that octet rule. So if we were to draw the electron diagram for magnesium, its outer shell would look like this. Now that's when it's neutral. However, magnesium is easily able to become an ion. It wants to give up those 2 electrons. When it does that, it becomes positive. Thus, its oxidation number is 2+. Also, when looking at oxidation numbers, we notice that some of them have multiple oxidation numbers. Some of them are the special ions that we looked at in class. Oftentimes you can look up an oxidation number in a special chart. Any of our transition elements in the periodic table could be considered a special ion and may have multiple oxidation numbers. If there is something with a special oxidation number in class in a quiz or test, we will make sure you know which ones they would be available for a type of reaction. And this concludes this podcast episode.